and begin. Fortunately, it seems as though I will be able to see my work this time, so we shouldn't have so many issues where y'all are always asking me to move my paper up or down. Okay, before we get started, are there any questions? All right. So let me give a recap of what we did yesterday. So yesterday, we covered two topics. The first one was we discussed how to solve separable nonlinear equations. So just to recall, first order, separable first order. So a general separable first order nonlinear differential equation will look something like dy dt is equal to some function f of t and y. Can someone tell me what the definition of a separable first order differential equation is?
So you can separate the function into like one term with just one variable, and then another term with the other variable in the differential.
Exactly, exactly. So here, a priori, this could be some messy function involving t's and y's, maybe multiplied together or something complicated. But if you can end up writing this as either, say, m of t, which is some function of t, plus n of y, dy over dt, equaling 0, or if you prefer to actually literally separate your variables, maybe you'd prefer writing it as n of y dy being equal to m of t dt. Either one of these are acceptable ways to think about a separable differential equation. Well, so this is the definition of a separable differential equation. You start off with something general like this. Can you write it in this form where this is only a function of t and this is only a function of y? And if you can separate your variables like this, then we discussed how to solve these differential equations. You literally just take antiderivatives. You take the antiderivative over here, or of the y term with respect to y, and you take the antiderivative of the t term, or the function in terms of t, or x, whatever variable we're choosing. So we essentially know how to solve separable differential equations. Okay. The second thing that we started discussing is we started discussing the existence and uniqueness theorems. Now, these are related to some of the deeper questions about differential equations. Mostly, we've been looking at small classes of differential equations and seeing if we can kind of brute force our way to a solution. But these existence and uniqueness theorems, if we are able to kind of get to them, would give us some strong kind of underlying basic facts that we can use, like this differential equation that I'm considering does have some solution, even if I have no good way to write it, or perhaps does not have some solution. So any question on what we were doing yesterday involving these two topics? And we only started this one. I'll get much further on this one today. No? Okay. Oh, also, I should just mention, I posted a new homework that is associated to separable differential equations this morning. I should have posted it yesterday. I need to be more on top of posting homework regularly the day that I cover the lecture. So I'm sorry about that. Okay. So what we're going to do today is we're going to discuss section 2.4 much more thoroughly. So 2.4 is existence and uniqueness theorems. And what we'll see is that the existence and uniqueness theorems have quite different forms based on whether you're considering nonlinear differential equations or linear differential equations. And so this is one way of thinking about the differences between those different classes of differential equations. Okay, so what I'm going to do first is I'm going to write down the existence and uniqueness theorem for first order linear differential equations. Theorem 2.4.1. Existence and uniqueness for first order linear. I should just stop saying ODE because we're pretty much never going to work with partial differential equations. Okay, so here is the theorem. Recall that a first order linear ODE is of the form, I'll put this as a side remark, y prime plus p of t y is equal to g of t. So this is the type of equation we're considering right now. So the theorem is, if p and g are continuous on some interval from a to b with t0 inside this interval, then there exists a unique solution, y is equal to a phi of t, such that, first of all, y satisfies the differential equation, and y also satisfies the initial value problem, y of t0 is equal to y of 0, and moreover, y is equal to phi of t is defined on this interval. So what the theorem in the book is written is this chunk. This is maybe a remark that I'll come back to.
Sorry, can you reread the third line of that?
This one?
No, the one above it.
Right, so P and Q are continuous on an interval from A to B with T0 inside A to B. Then there exists a unique solution.
So the little backwards E with an exclamation point, that means there exists.
Yeah, so this is some notation from the discrete math. So this big E backwards is exists, and the big E backwards with an exclamation point is there exists a unique solution.
Thank you.
Yeah, sure. Okay. Any questions before I discuss the proof? So the proof goes as follows. Before we begin the proof, and really what this proof relies on is the fundamental theorem of calculus. So first, recall from probably long ago for most of you, the fundamental theorem of calculus. And this is going to be the first part of the fundamental theorem of calculus. So let f be a continuous real function on A to B. This means its domain is A to B, this closed interval. So then we define a new function. Let f of x, big F of x, be equal to the definite integral from A to this indeterminate x of f of t dt. Then f is I'll put uniformly continuous. Perhaps all that you should remember is that f is a continuous function on a to b. It is differentiable on the open interval a to b. And what's the last fact? What is its derivative?
F of x.
Yeah, little f of x for all x inside a, b, right? So all this is probably recollection from when you first took calculus, but the point is, given little f a continuous real function, then we can by force write a continuous function which is its antiderivative on this interval. Maybe we can't express f of x in terms of elementary functions. It doesn't matter. We are able to write down a function defined in this kind of wonky way whose derivative is little f of x. This is kind of the most general way to think about antiderivatives. And the critical thing is we require f to be a continuous function on this interval. Now, remember that when we were doing our existence and uniqueness, several times for the general case, we actually had to rely on the fundamental theorem of calculus to find antiderivatives to things. And so these requirements that P and G be continuous functions are precisely there in this theorem so that I can correctly apply the fundamental theorem of calculus. Any questions about this? Just about the fundamental theorem of calculus, or is this, I mean, I think it's reviewed. Okay, so let's continue on with the actual proof. Or at least a sketch of the proof. Sketch of proof. So first, let's do existence. The point is, what's our general technique for solving first order linear differential equations?
Integrating factor?
Exactly, we need an integrating factor. So the technique we use is to find an integrating factor mu of t such that d over dt of mu of t is equal to p of t times mu of t. And if you recall how this discussion goes, essentially what we're eventually trying to solve is something like, well, once we've written something like this, we're going to be writing down expressions like mu of t is equal to c1 times e to the antiderivative from t0 up to t of p of z dz. So mu of t, so essentially what we're saying is this mu of t satisfies the above differential equation as long as what? Well, I need to apply the, if I want to take the derivative of this thing, I want to be able to use the fundamental theorem of calculus, right? What do I require for the fundamental theorem of calculus to apply?
Is it for it to be continuous?
Yes, I must require P of z be continuous. On some interval. So if P of z is not continuous, then when I write this expression, I don't actually know how to take this derivative. The fundamental theorem of calculus can't help me if I write this symbol, but this function's not continuous. On the other hand, if P of z is a continuous function, then I can apply the fundamental theorem of calculus, and when I take the derivative of this, I get back c1 e to this thing times the derivative of this thing, which is going to be P of t. So this thing satisfying this differential equation depends on P of t or P of z, it doesn't matter, and this is just a dummy variable, being a continuous function. Uses FTC. Okay? Is it clear now how I must require P of t to be continuous in order for me to find an integrating factor which works?
Yes.
Excellent, thank you. So remember, there's one other point when we are going to try to actually integrate something. Once we have found a correct integrating factor, our equation becomes d over dt of mu of t times y of t is equal to mu of t times g of t. And then when we take antiderivatives, we end up with mu of t, y of t is equal to, once again, this integral from t0 up to t of mu of s, g of s, dt plus c. Once again, what is a condition that I must demand such that when I take the derivative of both sides, I recover this?
U of t has to be continuous.
Yes, g of t has to be continuous. More particularly, this whole function, mu of s, g of s, has to be continuous. But we already know mu of s is continuous on our interval. And as long as g of s is continuous, then the product of two continuous functions will be continuous. So in order for d over dt of both sides, so maybe I'll write this as star and star star. In order for d over dt of star star to be equal to star, I need FTC, so I need mu of s, g of s to be continuous on an interval. Since mu of s is continuous by our assumption on P, we must require G to be continuous on an interval containing T0. Okay. Oh, it's very close to being off the edge. There we go. So essentially, the existence part of this proof, all that we're doing is we're checking that as long as these things are continuous, then we're allowed to write these expressions, and then using the fundamental theorem of calculus, their derivatives are what we need them to be. And that just relies on P of t and G of t being continuous functions. Once they're continuous, I can write all these things down, and the solutions that we discussed 3 days ago are all valid. Thus, we have existence. The uniqueness, I'll just kind of sketch the argument. There are two things that don't seem to be unique. For one, the mu of t is not unique because we could pick any constant times, I'll call it C1, e to the antiderivative t0, well, integral t0 up to t of p of t, or p of s ds. So mu of t is not unique because we can play around with this constant and all of these functions will still satisfy the required differential equation. And moreover, this function over here is not unique because I have some second constant. Mu of t, g of t, oh, sorry, y of t being equal to t0 up to t of mu of t, g of t. Oh, shoot. Mu of s, g of s, ds, plus c, c2. This is not unique, or this makes the solution not unique. Solution. So the point that I want to make here is that the non-uniqueness of mu of t doesn't matter at all, because in our final expression, we'll have y of t being equal to 1 over mu of t times the antiderivative, or the direct integral from t0 up to t of mu of s, g of s, ds, plus c2. Now, let's look at this function right here. If I change mu of s by multiplying it by a constant, well, I'll be multiplying in the numerator by some constant over here, and I'll be multiplying in the denominator by some constant over here. And so I can pull this constant out of the integral, and it will cancel with the constant over here. So this term is independent of what constant C1 I chose to multiply e to the t0 up to t p of s ds by. Is that clear?
Yeah.
Changing mu of t by multiplying a constant won't affect this expression. And then over here I'll get some expression c2 over c1 times 1 over mu of t. The point is, c2 over c1 is uniquely determined by an IVP. That is, if I demand that y of t0 is equal to y0, then that will uniquely determine the constant in front of the 1 over mu of t term. And so then we have uniqueness. So this function is unique, and this function is unique once you specify an initial value problem. Okay, so this is the discussion of uniqueness and existence on some interval. Yeah, sorry, I didn't see this question. Oh, sorry, I've not been looking. We have existence on an interval containing t sub 0. Yes. Okay. Are there any other questions that weren't answered in the group chat and that I should answer before we move on?
I'm kind of confused about the relationship you're outlining between the ratio of the two c values and 1 over mu of t. Like, what are you trying to say there?
I'm trying to say that it looks like we could choose a different c2 and a different c1 and get different functions that satisfy the differential equation, which is true. Any value of c2 and any value of c1, as long as they're not 0, will give me a function which satisfies where's my, yeah, it'll satisfy y prime plus p of ty is equal to g of t. But the point is, once I specify a particular, you can't see it. Once I specify an initial value problem, that is by specifying that y at t0 is equal to y0, then that will force this thing, which looks like a ratio of two things that could possibly, different choices of C2 and C1 could solve the differential equation, but there's only one value of this ratio that will solve both the differential equation and such that when I plug in t0 to this whole function, I'll get some specified y0.
Okay, thank you.
Yeah. Okay. So there are some important notes that I want to make. Important note. And that is these types of functions from t0 up, let me write it slightly differently. If f is continuous on the interval a to b, then this function f of t being equal to t0 up to t of f of s ds satisfies the FTC for all t0 and t inside AB. In other words, what I'm really saying is the fundamental theorem of calculus is able to define antiderivatives of functions on the biggest possible interval that is available to you. So you can kind of extend solutions as far as they can possibly be extended. What do I mean by that? Essentially, what this is saying is that the solution y is equal to phi of t can be defined on the largest interval containing t0 on which p of t and g of t are simultaneously continuous. So maybe an example kind of will help with this. Let's take this example of y prime plus tangent of ty being equal to sine of t. And I want to solve the IVP y of pi is equal to 0. So where is sine of t continuous?
Everywhere, right?
Yep, sine of t is continuous everywhere. Very good. Where is tangent of t continuous? Sine of t continuous everywhere. What about tangent of t?
Like at pi on 2,
Yeah,
and then at intervals like that?
Exactly. It'll be negative pi over 2 all the way up to pi over 2. And then it'll be continuous on pi over 2 all the way up to 3 pi over 2. And then so on and so forth. And it'll be continuous on all these intervals down here, like negative 3 pi over 2, negative pi over 2, right? So these are the baskets, or the intervals on which tangent of t is continuous. Now the point is, the existence and uniqueness theorem for first order linear differential equations essentially guarantees you a solution. Well, okay, first of all, it can only guarantee us a solution kind of locally. So if we're looking for y of pi being equal to 0, we need to look for the biggest interval on which both sine of t and tangent of t are continuous, containing pi. Well, pi is in here. And then sine of t places no restrictions because it's continuous everywhere. So what I can say is that we can find a unique solution, y is equal to phi of t, solving the differential equation and then satisfying the initial data. Such that the domain of phi of t is equal to pi over 2 to 3 pi over 2. So it has kind of the biggest domain possible. Is that, maybe this sounds kind of trivial, but I think it'll be much more interesting when we go to the nonlinear differential equations, where this is definitely not the case. So are there questions here about this important fact that solutions to linear ODEs can be, they have solutions on very large intervals?
So could there potentially be solutions elsewhere? We're just only guaranteed the existence of one in that particular bounds?
So there would also be solutions to the IVP, say y of, I don't know, let's do 1 is equal to, I don't know, 10. This is just some initial data that I picked. Now 1 is going to be inside this interval. So I am guaranteed by the fundamental theorem, or by the existence and uniqueness theorem, I'm guaranteed a phi of t that satisfies this differential equation and satisfies this initial condition, such that the domain of phi of t is negative pi over 2 all the way up to pi over 2. Does that answer your question or not really?
Yeah, that does. Thank you. So it kind of just depends on what the like the existence of something depends on the initial data being
exactly present. The thing that you have to compare is you have to write one function as look at all the places where it's continuous, write your other function all the places where it's continuous, and then put your initial data into one of those baskets, and then you can expand the domain of the function to be the biggest thing such that it's still inside the domains of continuity of both functions. Does that make sense?
Yeah, thank you.
Yeah. Okay, great. Any last questions on this? Okay, so the very interesting point is the situation is dramatically different for nonlinear equations. Exclamation point. 2 exclamation points. The situation is dramatically different for nonlinear. Okay, so the thing is, we do have an analogy of the existence and uniqueness theorem. We do have an analogy. We do have an existence uniqueness theorem. So we do have one, and I'll write it down, and we'll get to the proof later on in the course. I think it's in chapter 2.9 or something like that. So reasonably soon, we'll be talking about existence and uniqueness for nonlinear ODEs. But let me write out the form of this theorem. Theorem 2.4.2, existence, uniqueness for nonlinear first order ODE. So remember that the general form of a, well, yeah, someone tell me, what is the general form for a nonlinear first order ODE. I'm going to be able to write it as dy over dt is equal to what?
F of t and y.
Yeah, f of t and y. Actually, this isn't the most general first order ODE because I could get even worse by having like squares of dy over dt. So that could be, it could be even worse, but let's deal with this collection of first order nonlinear ODE. Okay, so here is the existence and uniqueness theorem for these. Let f and the partial of f with respect to y be continuous on some rectangle.
Can you move up?
Oh, yep, thank you. And here we've got two pieces of data that we need. Remember, these function f of t and y is a function of two variables. So if I'm deciding that it needs to be continuous, I need to give you a range in t and a range in y. And gamma less than y is less than delta. Let's assume that both of these functions are continuous on some rectangle in the ty plane containing t0, comma y0. This is going to be the point associated to our initial data. Then there exists some interval which is of the form alpha, which is less than t0 minus h, which is less than t, which is less than t0 plus h, which is less than beta. Oh man, this is going to be a mess because now I have to write it on the other side. Sorry. Terrible, terrible board work. So we have assumptions. Let me just rewrite some stuff. So assume f and partial y are continuous on alpha is less than t less than beta and gamma is less than y less than delta. Then there exists an interval inside the alpha beta interval. So I'll write it alpha is less than t0 minus h less than t0 plus h less than beta. And there exists a unique solution, y is equal to phi of t, to the IVP y prime is equal to f of t y and y of t0 is equal to y0. Okay. So let's digest a little bit what is going on here. First of all, the conditions that we demand of the function f are more stringent. Not only do we need continuity of the function f, we also need continuity of its partial derivative with respect to y. Okay? And then the second extremely important thing is that we do get some solution, which is both it exists and it's unique for solving this differential equation and satisfying the initial data. But this line is weird. This line is telling me that this solution is somehow very local. We might not have control over the domain on which this solution is defined, because all this theorem tells us is there's some interval, t0 minus h less than t less than t0 plus h, which is inside the interval AB, on which this solution is defined. Notice that the attempted analogy that we would try to say if we thought that the previous theorem generalized exactly is we would guess that we could have a solution defined from alpha to beta. where t ranges between these two values, because on this domain and on this domain, both of these functions are continuous. But it's not true that we can extend our solution to the entire t interval alpha to beta. That is not the case. So the picture for the first order linear is that solutions can be extended as far as possible, and it's kind of easy to see how far you can extend solutions. Here, for nonlinear differential equations, the idea is there's some small neighborhood around t0 where your solution is valid. And it may be very difficult to find out where your solution is valid, and it might be a very, very small neighborhood. Okay, this is kind of a complicated thing, so I think it's best illustrated with examples. So I'm about to do two really interesting examples, but before I do that, are there any questions just on the statement of the theorem? Should I move on to some examples?
Yeah.
All right, example time. Okay. As our first example, we'll take an example that's more or less worked out in the book over two different sections. So what we're going to look at is the following initial value problem. By the way, when I say initial value problem, I mean a differential equation and initial data. So hopefully that's been clear, but if not, that's what I mean. So let's try to understand the initial value problem, I'll use dy dx being equal to 3x squared plus 4x plus 2 over 2 times y minus 1. What kind of differential equation is this?
Nonlinear.
It is nonlinear, it is first order, and
Separable.
it is separable. So you already know that this is going to be nice from the perspective of us being able to find some concrete answer, basically, right? Moreover, my functions in terms of x and y are just polynomials. So we know that we're going to be able to find elementary antiderivatives of both of these functions just in terms of polynomials, right? So this is like the nicest separable case. And it'd be very easy, and we will write down an explicit form of an equation that any solution must solve, right? Essentially, as we discussed last time, we'll get implicit solutions. We'll see this. Okay, and then the initial data that we're going to consider are either y0 is equal to -1 or y0 is equal to +1. Okay, so the first thing that we should look at is what do we know, or what do we see for existence and uniqueness? So if we're examining existence and uniqueness, we're looking at this function of x and y and asking, where is it continuous? So where is this function continuous?
It's continuous everywhere except like y equals 1.
Exactly. This is a rational function in two variables, but still, it's a rational function. And rational functions are continuous everywhere except where the denominator has zeros. So f is continuous away from y is equal to 1. What's the derivative of this function with respect to y? The partial derivative? Well, the 3x, all the stuff involving x just looks like a constant, right? So it's really like 3x squared plus 4x plus 2 all over 2 times the derivative of 1 over y minus 1. So what's the derivative with respect to y of 1 over y minus 1?
Would it be like ln of like y minus 1?
That would be the antiderivative. The derivative is a little more simple.
Negative
Negative
1 over y minus 1 square.
Exactly. Right? If we take the derivative of y minus 1 to the negative 1, we bring down the negative 1, you have y minus 1 to the negative 2, and then that's this. Okay, where is this function continuous?
everywhere except y equals 1.
Yeah, exactly. It ends up giving you the exact same answer as you had up here. It's continuous away from y is equal to 1. So let me plot the x and y axis, the xy plane. This line at y is equal to 1 is a bad line that we have to avoid. So just looking at this right now, let's consider the IVP with initial data y0 is equal to negative 1. So what is the point 0, comma, negative 1? Well, it's this point right here. This is 0, negative 1. Can we apply the existence and uniqueness theorems for this initial value problem?
Yes.
Yes. You can fit a box around this point which avoids the bad locus. The bad locus here is y is equal to 1. So there is some box here where both f and the partial of f with respect to y are continuous functions. So theorem 2.4.2 says there exists a smaller box or a smaller interval in x that is a comma b with x0, which is equal to 0, 0 inside ab, on which I get existence and uniqueness of a solution. So somewhere in here, I can find some solution to this initial value problem. And it's not necessarily the case that I can extend it to the whole domain where f and partial of f are continuous functions. Okay? So to see more clearly what's going on, let me draw the slope field, or not really the slope field, but integral curves of the slope field. So this is also done with more accuracy in section 2.2. So the book draws this, and I would say probably if you have it available, look there instead of at my terrible drawing. But nonetheless, I'm going to try. The slope field has integral curves, that is, curves satisfying it, which look roughly like this. Roughly, so is it understandable what I'm kind of referring to when I say that this is the slope field? I mean, what I mean is that if I pick any point, the slope field lies tangent to the integral curves that I've drawn. Is it okay? So now let me show you kind of what's going on. Let's say this is our point 0, 1. Well, as you can see, the solution here could only possibly be defined up to here. Like there's some bound in the x axis past which I couldn't possibly extend this solution. It looks like I could probably extend this solution arbitrarily far to the right, because it just seems like it kind of goes, but maybe that's not true either. But at the very least, we see that this solution cannot be extended arbitrarily far to the left, because the only thing for this solution to do is to curve up this way, and then it doesn't pass the vertical line test, right? It's no longer a function if I extend this solution somehow past this line. Or if I try to think of this as being a solution parameterized by t, once I kind of pass this turn, I no longer get a function in terms of x. So what this means is this function over here, even though the functions f and partial of f are continuous on this huge, massive rectangle, that doesn't mean that I can extend a solution along this whole domain. I can only extend the solution up to here. The solution can only be defined in an interval which stops at this point. Is that, do you understand what I'm trying to display to you here?
Sort of.
Sort of, okay. Well, that's a start. Okay, and an important thing to note is that this bad locus that we found, y is equal to 1, exactly corresponds, if you believe my terrible drawing, to the place where the slope field is totally vertical. So in a certain sense, we can think of this discontinuity in f and partial of f with respect to y as carrying the data that over here, the slope field is vertical. So any function satisfying the slope field around this point, or any solution curve, isn't a function because it doesn't pass the vertical line test. And we can go even a little further. So let's keep this picture around. I'll bring it back in just a moment. So now let's consider the IVP around y0 is equal to 1. So this is asking us to solve with uniqueness and existence the initial value problem where our box must contain this point 0, 1. Question: does theorem 2.4.2 apply?
I would guess no.
No,
Yeah.
it does not. No, there is no rectangle around 0, 1, which avoids the bad locus, y is equal to 1, where f and partial of f with respect to y are discontinuous. Right? No rectangle, no matter how small that you try to draw it, or no matter what weird rectangle you try to draw, all of those rectangles will intersect this bad line, y is equal to 1. Do you agree?
Yeah.
Sorry, this handwriting is pretty bad. I apologize, but hopefully the picture is the better thing to see here. So this means that the fundamental theorem of, or not the fundamental, that the existence and uniqueness theorem does not apply, and we can find very explicit examples. So to solve this differential equation, dy over dx is equal to 3x squared plus 4x plus 2 over 2y minus 1. Well, you know how we solve this. You separate your variables, you integrate both sides, and you get left with the following equation. Y squared minus 2y is equal to x cubed plus 2x squared plus 2x plus c. What's c going to be? Well, we must solve this y0 is equal to 1. So if I plug in zeros for all the x's, and I plug in ones for all the y's, I get -1 is equal to c. So c is equal to -1. So what I have is y squared minus 2y is equal to x cubed plus 2x squared plus 2x minus 1. So here is not a solution, but an equation which implicitly defines solutions, right? And what I want to do is I want to solve this for y to try to get an actual solution. How do I solve this for y? How do I get rid of this messy y squared minus 2y?
Can you use completing the square?
Exactly. Very good. Complete the square. And what I get is y squared minus 2y plus 1 being equal to this whole thing, x cubed plus 2x squared plus 2x minus 1. Minus 1 plus 1, so it'll just be this. So y minus 1 squared is equal to x cubed plus 2x squared plus 2x. And then I can now solve y is equal to plus or minus the square root of x cubed plus 2x squared plus 2x plus 1. Okay, so here is this is kind of the solution. But it's not just one solution, right? It's actually two solutions, depending on whether I take the positive or negative branch of this square root. So let's examine the picture again. Where's my picture? Things visible here. Okay, so this chunk right here is the positive branch of the square root. This is y is equal to square root of blah, blah, blah plus 1. And this over here is the negative branch of the square root. Y is equal to negative blah, blah, blah plus 1. And notice these are two solutions. Both solve the differential equation, and they have the same value at 0, 1. In other words, I have two solutions to this IVP. One is the positive branch of this square root, one is the negative branch of the square root. So solution, even to the IVP, is not unique. Okay? So let's kind of, to recap, there are two important things. First of all, in the case of first order linear differential equations, first of all, oh, sorry, I've said that twice now. Second, it should be part A. Part A is that solutions to IVPs are unique and they exist. So we have kind of this strong existence and uniqueness. And second of all, these solutions can be extended as far as the functions are continuous. So somehow you can extend these solutions as much as possible. For nonlinear differential equations, first of all, you probably can't extend your solution very far. So you're only getting local criteria for existence and uniqueness. And second of all, when you're kind of forced to be on this bad locus, then you may not even have uniqueness for solutions to the initial value problem, as seen here. For this initial value problem, there are actually two solutions. That's not unique. Okay, that's kind of a lot to digest. Are there any questions here?
So if you were given an initial value, you can solve for a unique solution, right?
It depends on which, I mean, that depends on a lot of things. So you have to say several things. Which kind of problem are you considering? First order linear or first order nonlinear?
For the nonlinear.
For the nonlinear, next question is, does your IVP intersect the bad locus where either f or the partial of f with respect to y is not continuous?
Right, okay.
If you don't intersect that locus, then you do have some small area where you have existence and uniqueness. If you intersect this locus, this kind of bad locus, then several things could go wrong. You could have existence but not uniqueness, or you could even have failure of existence.
Okay, that makes sense. Thank you.
And even in the places where you avoid the bad locus, for instance, right, like if we're over here, if we're solving this IVP, we can avoid the bad locus. So we do have existence and uniqueness on some small interval, but not on a big interval, not here. We don't have a solution on this big interval. We only have a solution on this small interval, maybe something like this. But in any case, we can't have any solution where the left-hand side of the interval is bigger than this.
Mm-hmm. Right.
Do we check for existence and uniqueness before solving from here on out? Or before trying to solve, I guess?
I don't really know what to say exactly, because it's possible that always doing these computations may take you a long time. But on the other hand, right, like going from here all the way to here might take a while, and maybe some derivatives take a long time. So on one hand, if you're in a testing environment, I can't say that you should always test for existence and uniqueness all the time. But you should certainly know how to do it. And if you want to understand any equation deeply, it should probably be the first thing that you do. Like if you're going to spend, like if you're a professional applied mathematician or an economist or a biologist and you have a particular differential equation that you really care about, the first part of your analysis should be, where do we have existence, where do we have uniqueness, things like that. So it's a very important part of understanding a differential equation.
Okay, thank you.
Yeah, I don't know if that's a satisfactory answer in terms of when you're stressed on a midterm, but.
So what confuses me is that, like, I'm confused as to why this like problem that we have has like a solution that exists when y naught equals 1. Because like I thought we proved at the beginning that if y naught equals 1, then like you get 0 in the denominator and everything.
So right. Technically, I'm fudging a little bit here. What this is it's a solution which is differentiable on the open interval, like 0, comma, whatever. So it's differentiable here, and it satisfies the differential equation on this open interval. And its limit as x goes to 0 from above is our y of 0 is equal to 1.
Okay.
So it's like a solution on the open interval which agrees with the value of the function at a particular point if you take the limit, which is well defined.
Okay.
So one could count this as a solution, essentially, is what I'm saying. Great questions. Any other questions here? It's a complicated thing, so I'm definitely willing to spend a little time here on this problem. Okay, let me do another example, which looks very simple, but also illustrates some interesting behavior. let's examine the following differential equation. So solve the IVP. Y prime is equal to y squared, and y of 0 is equal to 1. Once again, is this linear or nonlinear?
Non-linear.
It's nonlinear because I've got a y squared. Is this separable or non-separable?
Separable.
Yeah, this is separable. So I can, in particular, write it as y prime over y squared is equal to 1, where 1 is my function of t, say. Let's think about what our theorems tell us. First of all, f of t comma y is equal to y squared. Where is y squared continuous?
Everywhere.
Yeah, this is continuous everywhere. And partial of f with respect to y is what?
2y.
2y, and this is also continuous everywhere. That's terrible, terrible handwriting, but the point is, this pair of functions is continuous on the whole ty plane, continuous everywhere. There are no bad loci that we have to worry about, okay? No bad loci. Nonetheless, let's solve this differential equation. Well, here, this is separable. We've got, or we could write this as 1 over y squared dy is equal to dt. Separated our variables. What's the antiderivative of 1 over y squared?
Negative 1 over y.
Yes, thank you. Antiderivative of 1 over y squared is negative 1 over y. What's the antiderivative of dt? Or 1, say?
T.
T.
Yep.
Plus
T
c.
plus c, exactly. We've got some constant here. We know that y of 0 is going to be 1, so we can already solve for c. If we plug in 0 for t, we get c is equal to negative 1 over, wait, sorry, let me solve a little further. We're going to get y of t is equal to negative 1 over t plus c. And I want 1 to be equal to whatever I get when I plug in for 0 here. So in particular, sorry, this is once again bad board work. 1 is equal to negative 1 over 0 plus c. So c is equal to negative 1. So a solution to this IVP is y is equal to negative 1 over t minus 1. Solution to the IVP. Okay. Over here, what does theorem 2.4.2 say, which is our existence and uniqueness for nonlinear?
We need the function and the partial derivative in terms of y to both be continuous.
Exactly. We need them to both be continuous, but guess what? They're continuous everywhere. So around any possible point, no matter what point I pick, here I picked 0, 1, but any point I pick, I can always find a rectangle around it such that the functions are continuous on all these rectangles. So the theorem applies, and I know that I can always locally find the existence and unique solutions, right? We know that. So we know, moreover, that this solution to the IVP is unique. Because we're in the case where we have existence and uniqueness because f and partial of f with respect to y are continuous everywhere. So we're good. Here's a question. On what domain does this function live?
Everywhere but one.
Well, kind of everywhere but one. That's not wrong. This function is defined everywhere but one, but the solution curve, y is equal to -1 over t minus 1, this really only makes sense for our purposes on the interval between -infinity and 1, right? Because we start off at t is equal to 0, and so we can't go up to 1, or we can't actually plug in 1. So we can go up to 1 and we can go below, right? Any negative number will work just fine here. But the solution to the IVP is defined here on -infinity to 1. Right? It's kind of like, you know, this looks very close to -1 over t, which, so this looks kind of like the family of functions looks kind of like, let me think about it. Something like this. But the point is, there's a vertical asymptote. So the only thing that really makes sense to consider, or should be at 0, 1. So we should have a curve passing through this point. It kind of doesn't make sense for us to consider any curve over on this side, because any constant would satisfy. We don't have the data of passing through a point to kind of help us along. So really, the solution should be thought of as living from -infinity to 1. This is where our solution to the IVP should live. Or in other words, we can't extend our solution, y is equal to phi of t, beyond -infinity to 1. So once again, we're in the situation where we started with a nonlinear differential equation. We checked the conditions for where f and the partial of f with respect to y are continuous. They're continuous everywhere, but we're still restricted in terms of the domain on which our solution can live. We can't extend it maximally. Like the idea of, like, one could hope by looking at f and the partial derivative of f with respect to y, we could hope, sorry, you can't see that. We could hope that we could extend the solution everywhere, but we simply can't. Right? This solution is only defined locally around this point. You can't extend it past 1 up above. So once again, we should only expect local solutions to nonlinear IVPs. And there, in general, is not a good way of determining the interval on which you can define your solution. For the linear ODE, you can exactly say, I can define it on this interval, right? If we go way back here, right. For this example, when we were dealing with sine of t and tangent of t, I know that I can define it on the biggest possible region where both functions are continuous, containing my initial point. I can define it on the maximal kind of area. For these problems, there's no immediate way without finding a solution to tell on which interval you might be able to define your solution. Fundamentally, we only expect local solutions. Any questions here? No? Is all clear? Okay. What I now want you to do is do some exercises. So what we've seen here is a pretty strong dichotomy between what we can expect from the solutions of linear first order ODEs and the bad behavior that frequently or almost always comes up when you're considering nonlinear first order ODEs. These next two exercises will provide further emphasis that solutions to first order linear ODEs are very special. So why don't you do these two things? Show that if y is a solution to y prime plus p of t y is equal to 0, then so is c times y for any c. Then the second part of the exercise is show that if y1 and y2 are two solutions to y prime plus p of t y is equal to 0, then so is y1 plus y2. And notice that once again, I am not giving you the full IVP. If I gave you an initial value problem, then solutions would be unique, but I'm not giving you an initial value problem. I'm just giving you a differential equation that these different functions solve. So why don't you give these a shot? And here I just want to remark that it is important that I'm not taking all first order linear differential equations, but I am setting g of t to be equal to 0 in both cases. Have people solved the first one? No?
No.
No? Okay. So let's talk about the first one. So we're assuming that y is a solution to this differential equation. So that means y prime plus p of ty is equal to 0. What does it mean for c of y to be a solution? Well, we need to check d over dt of c times y of t plus p of t times c times y of t. Check that this is also 0. Right? That's what it means to solve this differential equation. It's some function that when you plug it in for y, works. Well, but this is just c times y prime plus c times p of t times y, which is equal to c times y prime plus p of t times y. But what is y prime plus p of t times y?
0.
Yeah. Thus, cy is also a solution.
Wait, why did you multiply c to all the terms and not just to y?
Well, here what I did is I replaced y with c times y. So here I'm taking the derivative of c times y, and here I've got p of t multiplying c times y, my new function, right? Are you
Yeah.
okay with this step?
Yeah.
So constants pull out of derivatives. So I get c times y prime. And constants pull out of multiplication too. So I get this.
Yeah.
Now do you agree that this is equal to this by factoring out a c?
Yeah.
So is that okay?
Yeah. Yeah.
Okay.
So wait, but why'd you multiply c to 0?
Because this thing is assumed to be 0. Because I assume that y is a solution, which means this equation holds. Y prime plus pt of y is equal to 0.
Okay.
Do you need a couple more minutes on part 2?
Yeah, a couple minutes would be great.
Yeah, sure.
Can you go number 2 again?
I'm sorry, I didn't hear what the beginning of what you said.
2 again.
Still having issues. Do you want to see the problem? In any case, I probably need to start working through it since we only have 3 minutes left in class. If you want, oh, can you show number 2 again? Thank you. Yes, here's number 2. But just as soon as I showed it, I'm going to take it away because I'm going to solve this really quick. So what does it mean? Oh, shoot. So what does it mean that y1 and y2 are solutions? Someone tell me.
It means that they both satisfy the differential equation. Like if you
Right.
plug them in, it would be 0.
Exactly. So y1 prime plus p of t y1 is equal to 0, and y of 2 prime plus p of t y2 is equal to 0. And now what I need to check is I need to check that y1 plus y2 d over dt plus p of t times y1 plus y2 is also equal to 0. What's the derivative of a sum?
The derivative of the two parts, just
Yeah, it's the sum of the derivatives. So this is equal to dy1 over dt plus dy2 over dt plus, here we just multiply, p of ty1 plus p of ty2. Now collecting terms, this plus this is equal to what?
0.
This plus this is equal to?
Also 0.
So we get 0 plus 0 is indeed equal to 0. So the sum of solutions is also a solution. This is an extremely important fact. Because this is saying that the collection of solutions to a first order linear differential equation, not IVP, just differential equation where these are 0, can be given the structure of a vector space, which means I can add solutions together and still get a solution, and I can multiply solutions by constant numbers and still get a solution. So this is another extremely favorable property that solutions of linear first order, and it turns out it won't just be for first order, it'll be for linear differential equations, that we certainly don't have a result like this for nonlinear differential equations. So this is another way in which linear differential equations are extremely special.
And this is only applicable if GT is equals to 0, right?
Right, this is only applicable if GT is equal to 0.
Okay, thank you.
All right, that's about it for today. I will talk to you all tomorrow.
Thank you.
Thank you.
Have a
Thank
nice
you.
afternoon, everyone.
Thank you.
Thank you.